Welcome back. In this video, I'm going to solve exercises 4 and 9 of chapter 2. Exercise 4 is also an exercise about the subnorm, and we'll prove that the main result is that if a subnorm is non-negative, then it is necessarily the Minkowski functional of a convex set. Okay, so we consider a subnorm, which means that it's positively homogeneous and satisfies the triangle inequality, and we consider the set C of all elements of E whose image under P is strictly less than 1. So first question, we have to show that P of 0 is 0, and therefore homogeneity also continues to hold for lambda equals 0. Second question, we have to show that C is convex and 0 belongs to C. Third question, we have to show that if P is non-negative, then it's necessarily the Minkowski functional of C. And fourth question, we have to show that if P is non-negative, then there is an equivalence between saying that C is open, P is continuous, and saying that P is less or equal than m times the norm of X. And we have to give an example of a subnorm which is not continuous. Okay, so we know that P of lambda X equal lambda P of X for every lambda positive. So we take lambda equal 2 and X equals 0. We get P of 0 equal 2P of 0, which means that P of 0 equals 0. Okay, very straightforward. So this relation, in the definition, we assumed lambda is positive, but according to this, we still have P of 0x equals 0 P of X. Okay, second question. Consider, so we have to show that C is convex. This is straightforward. So we take two elements, X and Y in C, and a number T between 0 and 1. Of course, if T equals 0 or T equals 1, so we have to prove that 1 minus Tx plus Ty belongs to C. So if T equals 0 or T equals 1, there's nothing to prove. So since X is in C, then according to the course, P of X is strictly less than 1, and P of Y is strictly less than 1. Okay, actually, according to the definition, because this is C. So since X is in C, P of X is less than 1, and same thing for Y. And by a positive homogeneity, P of Tx equals Tp of X, and therefore this is strictly less than T, and same thing for 1 minus T times Y. So if I add the two, first I apply the triangle inequality. P of the convex combination is less than Ptx plus P1 minus Ty. There's the parenthesis here. But P of Tx is less than T, and this guy is less than 1 minus T, so the sum is less than 1. Okay, so therefore, according to the definition of C, Tx plus 1 minus Ty belongs to C. So C is convex. Okay, now, next thing. Y0 belongs to C because simply P of 0 equals 0, so it's less than 1, so 0 belongs to C. Third question, consider a positive number alpha and an element X in E. So what does it mean that alpha minus 1 of X or 1 over alpha X belongs to C? By definition of C, it means that P of this guy is less than 1, but since P is positively homogeneous, and I can put the alpha minus 1 outside, so I get alpha minus 1 Px less than 1, which means that P of X is less than alpha. Okay, and therefore, the set of alpha positive such that alpha minus 1x belongs to C is exactly equal to the open interval Px plus infinity. So alpha is here if and only if it's here. And therefore, the inf, what is the inf of this interval? It's precisely P of X. Okay. Here we use the assumption that P is bigger or equal than 0. Now, D, we have to prove the equivalence between three conditions. C is open, P is continuous and P is bounded from above by a constant times the norm of X. This is, yeah. So 2 implies 1 is clear because if P is continuous, C is precisely the inverse image under P of the interval minus infinity 1, or as well as the interval 0 and 1, open at 1. Same thing. So this is just continuity. 1 implies 3. So if C is open, we can use lemma 2.1, which tells me that we proved that in lemma 2.1 in the course that P of X is less or equal than M times the norm of X. 3 implies 2. In the previous exercise, actually, we showed that, so we can use the same reasoning, actually. So just use the sublinearity or the triangle inequality, if you like. So we write P of X is less or equal than P of X minus Y plus P of Y. So we subtract. And so it's the same thing actually works here. So the reasoning that we already used in exercise 3 shows that P is Lipschitz continuous. Okay, so that's it. So this proves that the 3 conditions are equivalent. Okay, now the last example, we have to give an example of a subnorm which is not continuous. So we can take, for example, the space of continuously differentiable functions on 0, 1, and we equip it with the supremum norm. So this is actually a subspace of C0, 1. And now we take P of U to be the supremum of the absolute value of U prime. Okay. In the exercise, in the lecture, actually, we mentioned that P is a subnorm, actually. So it's positively homogeneous and satisfies the triangle inequality. But the problem here is that if P of U equals 0, it doesn't imply that U equals 0. It only implies that U is a constant. Okay, so it's not a norm. And this is suppose that P is continuous, then we should have, by the previous question, P of U is less than a constant times the infinity norm of U. However, this is not true, because if you take in particular the sequence sine and t, then the norm of this sequence is 1, right? Because sine has the maximum at 1. So, and however, the derivative of un is n cosine nt. Therefore, and the maximum or the supremum of un prime t is n, because the maximum of cosine is 1 as well. So P of un equal n. So P of un is unbounded, whereas the norm is bounded. So this is a contradiction. Okay. Therefore, P is not continuous. Okay. So this concludes exercise 4. Exercise 9. We have a normal space E and a non-trivial element in the dual F, and we consider the kernel. So it's a particular case of a hyperplane, closed hyperplane. We have to find the orthogonal of M according to our definition of orthogonality relation. So this is by definition the set of G, if you like, in the dual, such that G of X equals 0 for every X in M. Okay. And second question, we have to prove that the distance from X to M, this hyperplane, is just f of X in absolute value divided by the norm of F, which makes sense because F is not 0. Okay, so we go back to the definition. The orthogonal of M is the set of elements in the dual that vanish on M. Okay, so that vanish on the kernel of F, which means that G of X is 0 whenever F of X is 0. Okay, so this means that this is the set of elements G whose kernel contains the kernel of F. But by exercise 1 that we prove, we know that if G is here, then G is a multiple of F. Okay? and conversely, of course. So the set is precisely the one-dimensional subspace generated by F. But of course, this subspace lives in E star. Okay. So this concludes the first question. Second question, how to prove this double inequality? So consider an arbitrary element x in E and put D to be this distance. If y is in the kernel of f, then f of y is 0. So f of x is f of x minus y, because by linearity. And by the fundamental property of linear bounded operators, this is less than the norm of f times the norm of the argument, which is x minus y. Okay, so x minus y is bigger or equal than f of x over the norm of f, but this is true for every y in the kernel. Therefore, the infimum of x minus y norm, when as y varies in the kernel, is bigger than this. So this is a lower bound. The infimum is the greatest lower bound. But the infimum of this quantity is precisely the distance, by definition of the distance from a point to a set. So we have this inequality. Now, to prove the reverse inequality, we do use a usual argument, since we cannot prove it directly. So we prove that f of x over norm of f is bigger, or if you like, f of x over norm of x is bigger or equal than d minus epsilon, if you like, or d is less than this guy plus epsilon, and then we'd let epsilon tend to 0. So consider an arbitrary positive number epsilon, which is less than the norm of f. We have to take it small enough, actually, but it doesn't really matter, because if it's true for every epsilon less than norm of f, we can later let epsilon tend to 0. Okay, but you'll see why I made this restriction. Okay. So the norm of f is by definition is the supremum of f of x as x is in the unit sphere, or if you like, the supremum of f of x over the norm of x as x is different from 0. Okay, so it's a supremum actually. So norm of f minus epsilon is not an upper bound of the set of f of x over norm of x. So this means that there exists an element, a non-zero element x0, such that absolute value of f of x0 over the norm of x0 is bigger than the supremum minus epsilon. Okay, so we can, if we multiply by norm of x0 and divide by norm of f minus epsilon, we get this, and this is why we assume that epsilon is less than the norm of f. Okay, so here, of course, the norm of x0, so x0 is not 0, so we can divide by it. Okay, and since epsilon is less than the norm of f, we can divide by it. Okay, so in particular, since this is not 0, and so f of x0 cannot vanish. Okay, otherwise we get norm of x0 strictly less than 0. So in particular, x0 does not belong to the kernel. And we know from the preliminaries in section 2.2 that the kernel of f has a one-dimensional complement. Okay, so it's easy to check that E is the direct sum of the kernel and the one-dimensional space generated by x0. We did that. How do you prove that? We have to prove two things, and we did this reasoning in the lecture. The intersection is reduced to 0, as you may check. And second thing, any element in X can be written as an element in the kernel plus a multiple of x0. Okay, so just do it, check it that to test your understanding. Okay, so we can write so every x in E can be written as an element y in the kernel plus lambda, and we have a formula for lambda actually if you are interested, but this is not really important. Okay, so yeah. Now, if we distinguish, if you like, between two cases, because we have to prove that the distance between x and m is, of course, x actually in this is true for every x. Okay, so there's a trivial case actually in this formula. If x is in M or in the kernel of F, then this distance is 0 and this is 0. Okay, so this is really a trivial case. So this equation is true if x is in M. Okay, therefore we have to prove it only for x not in M. Okay, so this is what we so we take an arbitrary x not in the kernel. So it can be written as y plus lambda x0, where lambda is different from 0 because now x is not in the kernel. Okay, so we can divide by lambda. Okay, so so we replace here x0 by x minus y over lambda. Okay, right? And we apply this inequality. So we replace in this inequality x0 by x minus y over lambda, and we get precisely this. Okay, and okay, now we multiply by lambda, if you like. So we get rid of this lambda, and by homogeneity, we can get rid of the lambda. So we can simplify by the lambda actually both sides. Okay, and since y is in the kernel, f of x minus y is precisely f of x. So after simplification by lambda, the numerator here is just f of x in absolute value. So we get norm of x minus y is less than absolute value of f of x over norm of f minus epsilon. And that's it. So the infimum is less than x minus y. And therefore d is less than absolute value of f of x over f minus epsilon. And since this is true for every epsilon less than norm of f, we can let epsilon tend to 0. And we get d is less or equal than absolute f of x over norm of f. So we have therefore proved double inequalities. So we have equality. Okay, so this concludes the exercise number 9 and therefore the video as well. And thus we have finished chapter 2. Now there are other interesting exercises in the chapter, but I don't have time to solve them all. And so, but of course, if you want to become a professional functional analyst, I advise you to try to solve all the exercises on your own. And if you don't succeed, you can read the solution in the on the website. Okay. So thank you for your attention and see you next time.